the properties to solve this integral equation. Yeah. Yeah. Then it's pretty straightforward. Yeah. We apply Laplace transform both sides. Yeah. Yeah. Right hand side, the basic formula. Yeah. So I hope you're familiar with Laplace of t to the n. This formula, okay, equals n factorial over s to the n plus 1. And here n equals 1. Yeah. Basic formula. All right, so then this integral part, it's a convolution. Yeah. Let's apply our convolution theorem. The product of two Laplace transforms. Product of the y part, that's the capital Y. Product of sine function. Yeah. So here. Right. Yeah, because we consider f and g, right? Yeah. So capital F and a capital G. Capital F times capital G. No, L. Yeah. G. All right. G is a sine function. Sine t. Sine t, sine omega t, right? Omega equals 1. Yeah. So that's why the formula 1 over s squared plus 1. Yeah. All right. So then, solving this equation, yeah, algebraic equation, we get a capital Y equals this expression. That inverse. To find the inverse, when you see that, you split the two terms in the numerator. Yeah. So after the split, 1 over s squared, 1 over s to the fourth, now you can use the inverse Laplace transform, use this formula. Yeah. The first one, t, right? Yeah. Yeah. So here I copy the, yeah, I cannot erase. Yeah. So here, this software, the annotation I did last time, I cannot erase this time. Yeah. So that part I cannot erase. So the formula, yeah. So that formula is just the same as this one. Okay. Yeah. That the inverse. Yeah. The first term t, right? Yeah. Second term, yeah. So you need to find appropriate factorial. What factorial? 3 factorial, right? 3 to the fourth equals t cubed. Now 1/6, yeah, because 3 factorial, that's 6. Yeah. So you get this. Yeah. All right. T plus 1/6 t cubed. Yeah. That's the solution. How about that? Yeah, it's a simple example. Yeah. But we can see, in this kind of integral equation, the convolution operation is important. Yeah. All right. Yeah. So that's this. Let's go to another important topic: differentiation and integration of transforms, Laplace transforms. Yeah. Yeah. So you may, right, integration, we did something in module 2, right? Yeah. So integral, remember the Laplace transform? Yeah. So here let's recall what we did in the module 2. So here we need to compare the difference. Sorry. Yeah. So let's think about the Laplace transform of the integral from 0 to t little f this function, okay? Yeah. Then capital F S over S. Okay? Yeah. Laplace transform of that integral. Then at the other side, division by S. Yeah. That's what we learn. Yeah. All right. Yeah. Derivatives. Remember, we have two derivative formula, right? Yeah. So Laplace transform of f prime s, right? Plus, minus initial value, right? Yeah. Then we have Laplace transform f double prime. Okay, that's our. This is the second time I received today. Oh, yeah. Let me. But this kind of, even I put it in the airplane mode, it's still there. All right. Yeah. That's our two formulas related to derivatives and integrals. Yeah. But here, these, differentiation formula and the integration formula should be different. Okay? Yeah. Yeah. Here, before we look at these, two new formulas, so here you can see in our old formula, where do we do the derivatives and integral? When we do we do this side, right? Yeah. Laplace transform inside that parenthesis, we do take derivative. Yeah. Here, inside Laplace transform, this parenthesis, we take integral. Yeah. All right. Then, how about the other side, right? Yeah. Derivative at the capital F side. All right. Integral, right? So here, there is a different way to do derivatives and integrals. Yeah. All right, so let's look at that. Let's start with the definition. Yeah. Yeah. From the definition of the Laplace transform. Yeah. Think about, how about we take, look at this equality, right? This equality is true all the time. Yeah. All the time for any s, right? For any s greater than 0. Yeah. So we have that. How about we take derivatives both sides? Okay? In calculus, we have a theorem like this. If you take the derivative this side, you just take derivative inside, okay? Yeah. Inside by the chain rule, right? Chain rule, derivative you apply on this e function, because only this e function contains s. Yeah, other function does not contain s. If it does not contain s, you treat it as constant. You treat it as constant, okay? So you just keep it, copy. Yeah. The s related to s part, you take derivative. Yeah. All right. Then the chain rule, you have -1, and you have an extra t by the chain rule. Yeah. All right. So then you simplify it. Okay. Yeah. Simplify it. So then you get this formula: negative Laplace transform t times original little f function. Here you can see the derivative operation you applied on the f function, then that's the same thing you apply Laplace transform, yeah, but you need to multiply a t to the original little f function, and you need a negative sign. All right. Yeah, that's a new formula. Yeah, but we apply derivative in a different way. All right. Yeah. So we hope this formula can help us. Okay. Yeah, can help us, in some special way. Yeah. Now, so we can, clean up a little bit. Yeah, try to reformulate. Make it look a little better. Yeah. But at the same time, we'll have an inverse Laplace transform version, right? Yeah. Because this one we can write inverse Laplace transform. Then apply on the derivative of capital F function. Then this side, multiply t, then negative. Yeah. Right? Yeah. So that's another nice formula. Yeah. So we have another useful tool we can apply when we take Laplace transform. But we need to, the main thing is you need to identify. So using your observation to identify the pattern, the structure. Yeah. Usually you may have multiple ways to solve, given a particular question. Yeah, because when you view it in a different way, based on your knowledge, so you may see, I see this structure, so then I apply this method. If you see a different structure, then your method will be different. Yeah. So here we have another way, so we can, if we find the structure fits the format of this formula, then we use this method. Yeah. All right. Show you some example. Let you see the power of this formula. Yeah. Here you can see the Laplace transform of these formula relatively hard, right? Yeah. Why? The denominator is something square. It's a square function. That make it a little hard. Yeah. All right. Yeah. But think about if our f of s is the function without derivative. Then we take a derivative. Okay? Then we get a square, right? But the numerator there is a s. Numerator there is s. That's this version. Okay? So you can see, by taking derivative, we get that version. Okay? Yeah. All right. So we start, because this version there is no square at the denominator. But the second one, if we take derivative, we will have square. Yeah. But at the same time, we will have s in the numerator. Yeah. The first one, we can try. We take derivative. Yeah, but a little harder. Yeah. All right. When we start, this is our. We just copy. Yeah, we just replace omega by delta. Beta. Yeah, beta. Yeah. All right. Then we apply this differentiation of the Laplace transform, this formula. Yeah. Okay. T, here we use this version. Okay. Yeah. T times derivative, that 2 beta constant times s over that. Very close. Then we divide it by 2 beta, both sides. Now you have this. Yeah, that's this formula. Oh, sorry. There is a t missing, right? Yeah. Last year I noticed that. Yeah. Because here we need to multiply that t. Okay? Yeah. Because there is a t here, okay, based on that formula. So here I copy from the textbook. Okay? That t is missing. Yeah. I noticed this problem last year. Yeah. All right. All right. integration of transforms. Let's look at another case. Yeah, integration. All right. Yeah. Laplace transform of integral, right? This is our old formula, right? Yeah. So for comparison, so here I copy. This is our old formula we learned before. So we take integral inside Laplace transform. You know, that L operation inside this side. Yeah. Not that S side. Okay, capital F, that S side. All right, so here, then, so look at, when we take integral at the capital F side, all right, now the little f, so this one, our old formula, this is our old one, we take integral at the little f place. The second one, a different version, take integral at a capital F side. Yeah. Then the little f side, division by t. Yeah. See? Yeah. Here you can find the rule, right? Derivative of f side, capital F side, then and the little f side multiplied by t, but we need a negative sign. Okay, don't miss that negative sign. And here we need integral at the capital F side. We do division by t at the little f side, but no negative sign. Okay, yeah. All right. Then the inverse version. Yeah. All right. The condition. Yeah. Yeah, because when you use this expression, you need to make sure when t goes to 0, this limit exists. Yeah. Extra condition. Yeah. Otherwise, you get something, you know, it does not converge at a 0. Yeah. All right? Yeah. So you need to, you know, check this condition. All right? Yeah. Another Laplace transform exists. That's the condition for make sure Laplace transform of little f exists. Yeah. All right. Yeah. Yeah. And the s, right? S greater than k. Yeah. Yeah. Okay. Yeah. K, this k, okay? Yeah, that k. Yeah. Otherwise, you know, Laplace transform does not exist. Yeah. All right. Here, the proof, okay? Yeah. Because you may ask, how to see that? How to see this formula, right? Yeah. You want to see? Yeah. Here, this is the proof. When we calculate this integral by, you know, this is the definition of the Laplace transform. Yeah. Okay, S tilde. Yeah. Yeah. Here, because inside the dummy variable, we cannot use S, right? Because this S, we treat it as a constant. We fix it. That little s in this formula, we fix it first. So it's a constant. Then, the dummy variable, we need to use a different notation. Yeah, so that's why we use S tilde. All right, so that's the formula. Then, there is an important theorem in calculus. So you swap the, you know, integral, because here, nested integrals. Yeah. 2 levels. Can you swap the, you know, the order of integration? Yeah. Here the order is the current order of the integration. You do integral with respect to the t variable first. After that, you do the integral with respect to S tilde second. Yeah. Yeah. So that Fubini theorem. So there is a very important theorem in calculus. Fubini theorem. You can switch the order under some condition. There is some condition. But condition, you know, here. We have it. Under certain condition. That means you can do integral with respect to s tilde first. After that, then integral with respect to t second. Okay? Change the order. Yeah. Then something new happens. When you change the order, something new happens. Yeah. Here, yeah, all right. So let's, now you see the change the order, right? Yeah. Because you do integral with respect to s tilde first. Then after that, you do integral with respect to t second. Okay? Yeah, that's the Fubini theorem. Yeah. Yeah, very important theorem in calculus. All right. Then, because with respect to s, your ft is a constant, you can take it out, right? Then you do integral. That's easy, right? Yeah. So then, yeah. After that, so definition. Yeah. After this, then you apply definition of Laplace transform by t. Yeah. That's the proof. Okay. Yeah. Here, this place, this, switch the order. Yeah. That's the Fubini theorem. Okay. Yeah. All right. Yeah. Yeah. It's a powerful theorem. Yeah. All right. Now, we have another good formula. Yeah. So these two formulas. Another pair of formulas we can use. Yeah. All right, C.3, examples. Yeah, since we just derived two pairs of important formulas. Now we need to use these two new formulas to solve some problems. Yeah. Examples. Integration of transform. That example first. Yeah. So let's copy the formula below. Yeah. Calculate inverse Laplace transform of this special function. Natural log of some function. Yeah. All right. That's the capital S side. Yeah. Right? Yeah. Inverse. Yeah. Think about that. Yeah. Yeah. Let's see how to understand the structure here. Yeah. 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 Can you? Yeah. The first thing. Can you see integral? Yeah. Right. So here. Yeah. Can we see? Yeah, this is a little hard to see, right? Yeah, because if we can match that structure, integral structure, or we use this formula, okay? This structure, then we can apply this formula. Yeah. But it's not easy to see. Yeah. How about, so this is our goal, okay? Our current goal. We want this function unknown. Yeah. But we want to have this structure. Yeah. Can we find capital G? Yeah. Yeah. Can we find capital G? How about we take derivative both sides? If you take derivative at both sides, the right hand side, you have something related to capital G, right? Yeah. So that is the, that is the fundamental theorem of calculus, right? But the different thing is, that S part is at the lower limit, not upper limit. Lower limit, you need to use negative sign, okay? Yeah, because at the bottom, minus. Yeah. Yeah. All right? Yeah. Lower limit, because by the fundamental theorem of calculus, you use the upper limit minus the lower limit. So the upper limit because at infinity you assume it's 0. Yeah. At infinity you assume it's 0. So then, yeah, you need a negative sign. Yeah. All right. So that's why you take a derivative. You have negative g of s. The reason is s appears at the lower limit. If s appears at the upper limit, then you don't have that negative sign. Okay, you have the positive sign. Then, right hand side you need to take derivative. Yeah, okay, yeah, you split the structure, the division. So you can split. This minus. Yeah. Yes. Then, derivative. Natural log, you can find it easily, right? Yeah. Natural log, yeah. Chain rule, yeah, here. First, second, yeah. All right. So you find the g function. Yeah. Yeah. G, you can, simplify it. Yeah. That's the g function. After you have g function, can you find little g? Yeah, because this is capital G. You need to find the little g function, right? Then you can use little g over little t. Yeah. So you need to find inverse Laplace transform of this capital G. Then we can see it quickly, right? Yeah, two basic formulas. Yeah. First basic formula, yeah, 1, 2. Yeah. Second base of a cosine, s omega, yeah, squared 2, yeah, constant. Okay, all right. That inverse little g 2 minus 2 times cosine omega t. Yeah. Then last step, yeah, divided by, this one, little g over t. Yeah, that's the. See, yeah. So you can see it is a powerful tool. Otherwise, imagine how to find the inverse Laplace transform. Yeah. Now, because you can take derivative, okay, you can. So here the harder part is, yeah, let's try to understand, yeah, because we need to learn from this example and make it in our experience. The reason it's hard, why? First, we need to understand why it is hard. The reason it is hard is because of this natural log. Okay? If you look at our basic formula, we don't know how to handle, inverse Laplace transform with that natural log. Yeah. All right? But the good property for this formula, yeah, all right, because when we take a derivative, natural log is gone, right? Think about. So our understanding. So why we want to connect to the derivative? The reason is we know when we take a derivative on a natural log function, then natural log is gone. This experience is important. Otherwise, how do you connect to, derivative integral thing, right? Yeah. Yeah. Here, our understanding, we know, the reason we want to connect to derivative integral, yeah, because derivative of natural log. Yeah. So then it becomes fractions, yeah, becomes the fractions like that. Then we don't worry about it. We can use our basic formula. Yeah. All right. Yeah. Then Lagrange's equation, yeah, solve, yeah, this special equations. Yeah. Laplace transform. Now you see, yeah. So in the Laplace transform, yeah. So let's try to look at how do we understand the structure of this equation. Yeah. Yeah. The difference here is 1 minus t here. See? Yeah. 1 minus t. Yeah. All right. Then derivative formula, but now you have t multiplier, right? T multiplier there, we need to use the differentiation formula. T, remember that? T, little f, right? Yeah. Yeah. Right? The differentiation. Take derivative at the f side. Yeah. This, you're separate. Minus, it's okay. One you have t, the other you don't have t. So you can get immediately. The part you have t, you can apply that differentiation, that formula. All right? Yeah, so this is the formula we want to apply. Yeah. When we apply, we want to use different little f. Yeah. Sometimes f prime, sometimes f double prime. Okay? Yeah. We need to use in different ways. Yeah. First, let's apply a Laplace transform. Yeah. All right. And these two terms, easy, right? Yeah. So we need to find expressions of the other two terms. Yeah. All right. First, yeah, this one, apply that formula. Yeah. Very easy. Yeah. All right. Then this one, yes, this one. Yeah. How to see this one? Yeah. So here I try to. Yeah. All right. How about yeah? This one comes from that. Yeah. All right. So here my understanding. Yeah. Let me show you. Yeah. If you cannot see it. Yeah. T y prime. Here we treat y prime as a little f, right? Yeah, y prime little f. Then it should be negative f prime. All right? Yeah. Then what is this capital F, right? This is the capital F. Because if we make this little f, then that is a capital F. Yeah? Because here we assume y prime as the little f in this place. Then capital F is by that formula. That's why we take derivative on capital F. That is the capital F. Okay? But remember, we need to add a negative sign. Yeah, so that's how we apply this derivative formula or differentiation formula. Yeah, whatever you call. Yeah, that's easy. Yeah, yeah. So you get this expression. That second term. This time we need to make f equals y double prime. Okay, then capital F equals Laplace transform of y double prime. Then we apply the second formula, right? Yeah. All right. So the second formula, so we have that. Now you know this capital F whole thing, you take derivative with respect to s, then negative sign. Yeah, this time, negative sign, that formula. Yeah. Then, after you simplify it, you get this number, this expression, plug in, yeah. Going back, yeah. Yeah. Yeah, because here, the calculation. Yeah. All right. Yeah. Yeah, but we need to add together. So here we want to add together. Yeah. All right. Okay. Yeah. 4 terms, remember? Term 1, term 2, term 3, term 4. Okay? Term 1, 2, 3, 4. Yeah. All right.
The middle term, s, negative s times y of 0.
Yeah.
For the Laplace transform t times y double prime.
Yeah, this one, right?
To the left.
Oh, look.
Yes. So
This.
one up. Yeah. Why is that middle term negative?
Oh, why middle? Oh, yeah. Yeah, all right, so let's see. All right, this middle term negative. Yeah, all right.
There's got to be a negative coming out somewhere.
Right, because when we do, yeah, all right, let's do the easy part first, okay? Yeah, because when we take derivative, this part relatively hard. Let's do the easy part first. Easy part, this term gone, right? All right. This term, negative, negative, positive, and S gone, right? Yeah, so this left, all right. Then the remaining, these two terms corresponds to the first term. Then you need to apply the product, right? The first one, yeah, negative, yeah, so you keep that then negative, all right? Yeah. So 2s capital Y plus s squared y prime, right? That's that. Good, yeah. All right, yeah. So yeah, relatively complicated, but we need to work on the easy terms first, yeah. And the hardest term the last. Yeah. All right, yeah. So finally, we need to, add up all these 4 terms. Yeah, this is number 4. Okay, that is number 4. All right. Yeah, cancellation, right? Cancel, yeah. So we get this expression. Yeah. First order ODE. Yeah. Here you can see in this way. Remember, so here I want to say something about this equation. Yeah. Before we try to solve it. Yeah. Remember, before this topic, we have the usual way we do. We convert ODE to algebraic equation, right? Remember, when we apply Laplace transform, we can convert ODEs to algebraic equations. But here you can see, ODE, after you apply Laplace transform, you still get another ODE. Okay, yeah, a little simpler. Yeah, first order. Originally you have second order, but now you have first order ODE. Yeah, you get another ODE. Yeah, it's not an algebraic equation. Okay, all right. Then separable, right? Yeah. So y s can be separated in this way. Yeah. Then, yeah. You get that. Yeah. Natural log, or what's, yeah, why is that? Oh, yeah. Yeah, so here, because when we take integral both sides, why is that? Yeah. Let me see. Yeah, little ln. Yeah. Oh, yeah, so here, I try to use some formula. Yeah. Yeah. So here the formula, if y equals this function, yeah, little ln inverse Laplace transform has this expression. Yeah. Okay. Yeah. Yeah. All right. Yeah. So then here, yeah. Yeah. So this y. How can we get? Yeah. Yeah. Anyway, all right. Yeah. All right. So let me try to understand. Yeah. So why we connect that? Yeah. But it looks pretty complicated. It's a well-known function. So this is a well-known function. Yeah. All right. Yeah. Let me see. I have some a few minutes. Okay, all right. Yeah, so we finish this part C. Yeah, yeah, finish this part C. Yeah, but let's do this way. Yeah, because in the midterm, yeah, let us do not include this part. Yeah. Do not include differentiation and integration part. Yeah, because we need to do practice, right? Yeah. I want to put this topic in our homework assignment number 3 after midterm. You need to have, plenty of practice experience before you can, put these questions in the test. Yeah. So midterm, so you do not need to worry about, questions. Yeah. Let me see. Let me clearly say in this way. Even convolution part. Okay. Yeah, because convolution, we also need to do practice, right? Yeah. Convolution part, I haven't assigned you any convolution questions. Yeah. So we need to put in our homework assignment number 3. Yeah. So you need to have, very good, the whole practice experience. Yeah. So I won't put these questions in our midterm. Okay? Yeah. Yeah. Convolution, after convolution. So convolution, differentiation, integration of Laplace transforms. Oh, how about other than that? Heaviside. Did we practice Heaviside function in homework assignment number 2? There is, yes.
There's a piecewise function.
Yeah, piecewise function. Yeah. So Heaviside, that included in the midterm, but we don't have that delta. Yeah, we don't have that delta, but delta not that hard, right? Yeah, direct. Yeah, direct. So delta not that hard. Yeah. So Heaviside delta function could be included in the midterm. Yeah, midterm. But Heaviside, so definitely I will give you one Heaviside question. Yeah, but delta not necessary because we have too many topics. Yeah, too many question types. Yeah.
If you can figure out the heavy side, the delta is a lot.
Yes, a lot easier. Yeah, yeah. But I feel because I only plan to give you 10 questions. 10 questions. I can only cover 10 topics, 10 special topics. Yeah, so probably not necessary to put the delta function. Yeah. All right. Yeah. So in that way, yeah. So that's our plan for the midterm. So then after midterm, you need another 2 homework assignments. Yeah. So the first assignment we practice, all these things here. Yeah. So the second assignment we need to practice, there are several other important topics. One is solving linear system. Yeah. Eigenvalue, eigenfunction. Yeah, linear system. That's an important part. Yeah, we need to.
Series solution.
Yeah, series solution also. But yeah, then Fourier is the most important topic after midterm. Yeah. So Fourier analysis, the most important topic after midterm. Yeah. Other than that, linear system, second important. Then series solutions, yeah, relatively simple, but calculation is very hard. Yeah, I mean the idea is so simple. Yeah, but calculation, very hard. Yeah, relatively small topic. So we're basically we have these three topics. Yeah. Fourier analysis, the biggest. Linear system, in the middle. Then the series solution, relatively small. Small, I only need to give you, small number of exercise question. In test, I only need to give you one question. Yeah, one question, let you just, do one. Do one should be enough. Yeah. All right. Yeah. All right. So let's take a 10-minute break. Still 7:10. Then we will do our review session number 1. Yeah. So I talk about selected questions. So not all the questions, because some questions are so simple. So I don't want to selected questions from homework quiz 1, quiz 2, and homework 1, homework assignment 1. Yeah. Yeah. All right. So.